if you want to take a vacation, take it before that date, because who knows what will happen.
Harvard astrophysicist Avi Loeb has published an analysis suggesting 3I Atlas may have catastrophically fragmented into at least 16 pieces near the Sun. New observations from November reveal jet structures and mass loss patterns that challenge conventional comet models. The data is quantifiable, the measurements are documented, and the questions raised demand answers before this interstellar visitor disappears forever. If you find this as intriguing as astronomers do, stay until the end. And don't forget to share your thoughts and subscribe for more clear, fact-based analysis. Let's get into it. Avi Loeb's recent calculations have identified a significant paradox in the observational data. To produce the mass loss rate measured during perihelion, 3I Atlas would need a nucleus approximately 14 kilometers in diameter. However, Hubble Space Telescope images captured on July 21st show a nucleus measuring just 1 to 2 kilometers across. That represents a discrepancy of at least 16 times between calculated requirements and observed dimensions. The numbers don't reconcile through standard physics. At perihelion, the object was losing material at a rate that accelerated from 330 kilograms per second in early August to nearly 2 million kilograms per second by late October. That's a 600-fold increase, equivalent to vaporizing the mass of 2 skyscrapers every second. For an object the size observed, this sublimation rate exceeds what solar radiation alone should trigger. The energy calculations present an equally puzzling picture. At perihelion distance, the Sun delivers approximately 700 joules per square meter per second to the surface. To achieve the observed outgassing through natural sublimation, 3I Atlas would need to absorb nearly all incoming solar radiation with maximum efficiency. Even under ideal conditions with a perfectly black surface, the mathematics require substantially more surface area than a 1 to 2 kilometer nucleus provides. Loeb's November 10th analysis proposes the comet must have fragmented into multiple pieces, each creating additional surface area to absorb solar energy. By breaking into at least 16 equal fragments, the collective surface area would expand sufficiently to account for the observed outgassing. Some researchers suggest thermal stress from rapid solar heating could trigger such breakup, similar to Comet Schwarzmann-Wachmann. Others note the timing and apparent symmetry raise questions about whether standard fragmentation models fully explain what occurred. The fragmentation hypothesis also addresses the acceleration anomaly documented in Harvard's tracking data. The object exhibited gravitational acceleration reaching 94 kilometers per day, squared at perihelion, substantially exceeding predictions based on solar gravity alone. If the nucleus fragmented, differential outgassing from multiple pieces could produce non-gravitational forces sufficient to explain the excess acceleration. When British Astronomical Association members Michael Butner and Frank Neveling released their November 8th and 9th images, the data became considerably more complex. Their photographs revealed structures that deviate from typical post-perihelion comet behavior. The images show at least 7 distinct jets emanating from the nucleus region. Most striking are the anti-tail formations, bright streaks extending approximately 950,000 kilometers directly toward the Sun. Anti-tails are rare but documented phenomena, occurring when debris particles align along Earth's line of sight. However, the density and organization of these particular structures have drawn attention from multiple research teams. The main jet extends more than 2.85 million kilometers, nearly twice the Earth-Moon distance. This represents a 1,000-fold increase in observable jet length compared to pre-perihelion measurements. Spectroscopic data indicates these jets contain ionized metals including cobalt and titanium, elements not commonly observed in such concentrations in comet outgassing. The distribution pattern of the jets appears organized, with several pointing toward fixed coordinates along the ecliptic plane. Photometric analysis shows the jets maintain consistent brightness profiles along their lengths, rather than the expected rapid dimming typical of dispersing gas clouds. Additional images captured by astrophotographers M. Yeager, G. Raymond, and E. Prosper on November 8th document similar structures from different observation angles, suggesting these formations are genuine physical phenomena rather than instrumental artifacts. Temperature measurements add another layer of complexity. Infrared observations detected thermal signatures suggesting surface temperatures exceeding 600 Kelvin in localized regions, significantly hotter than models predict for a fragmenting ice body at that solar distance. Some researchers propose that if fragmentation exposed fresh subsurface material with different thermal properties, this could explain the anomalous readings, though detailed modeling remains ongoing. Following perihelion, institutional communication regarding 3I Atlas became noticeably limited. NASA's public updates, which had been regular through September and October, decreased in frequency during November. The Mars Reconnaissance Orbiter's HiRISE camera has not released data, despite the object's trajectory bringing it within theoretical imaging range. The European Space Agency increased its observation schedule during the same period, deploying additional tracking time on ground-based facilities, though corresponding data releases have not matched the expanded observation effort. ESA's optical ground stations in Tenerife and La Palma reportedly redirected substantial telescope time toward 3I Atlas monitoring during the first 2 weeks of November, yet the resulting datasets have not appeared in public archives. Unofficial reports circulating through astronomical communities claim at least 3 military reconnaissance satellites were repositioned during late October, though official confirmation has not been provided. Some analysts have noted that both China and Russia appear to deploy tracking programs coinciding with 3I Atlas's perihelion passage. China's Purple Mountain Observatory reportedly allocated observation time during the critical November window, while Russia's Institute of Astronomy increased its monitoring frequency. These observations remain unverified through official channels. The U.S. government shutdown that occurred during this period has been cited as explanation for communication delays, though internal briefings reportedly referenced 3I Atlas specifically in the context of restricted information protocols. Such restrictions are not unprecedented for unusual astronomical phenomena, particularly when initial data presents interpretive challenges requiring interdisciplinary review before public release. On October 24th, radio telescopes detected hydroxyl absorption lines in the object's vicinity, standard molecular signatures associated with water sublimation in comets. However, the signal characteristics reportedly included patterns some researchers found noteworthy. The October 24th detection allegedly showed narrow-band characteristics, with periodic intensity variations over a 6-hour observation window. If confirmed, such periodicity could indicate rotation-modulated outgassing from localized sources rather than uniform sublimation across the nucleus surface. With institutional analysis largely confined to internal channels, scientists have been working to determine which physical models best explain the observed phenomena. Standard comet outgassing produces jets traveling at approximately 0.4 kilometers per second. The jets documented in November appeared within days of perihelion passage. For natural processes to create such extensive structures, so rapidly would require outgassing velocities significantly higher than typically observed, roughly a factor of 10. While superheated gas can reach higher velocities under extreme conditions, sustaining such velocities requires energy input beyond what solar heating typically provides. Chemical rocket exhaust, by comparison, moves roughly 10 times faster than natural comet jets, providing comparative benchmarks for evaluating propulsion mechanics. The anti-tail density measurements present another analytical challenge. The observed concentration appears approximately 1 million times denser than standard solar wind interactions would generate. Several mechanisms could potentially explain this: particle alignment along magnetic field lines, compression through shock waves, or debris clustering through gravitational interactions. Each has precedent in solar system observations, though none perfectly matches 3I Atlas's documented characteristics. The mass loss calculation remains the most persistent anomaly. At 50 billion tons per month, the object is shedding material at a rate approaching estimates of its entire remaining mass, suggesting complete disintegration within months. Yet tracking data shows the object maintains a coherent trajectory with ongoing jet activity. Avi Loeb has raised questions about whether technological processes could account for some observed characteristics, framing this as a hypothesis worthy of investigation. The scientific method demands consideration of all explanations consistent with data, then systematic elimination as evidence accumulates. At present, both natural and non-natural explanations remain mathematically viable. Other researchers maintain that thermal stress fragmentation remains the most parsimonious explanation. Comet Linear fragmented spectacularly in 2000, while Comet Ison disintegrated during its 2013 perihelion passage, demonstrating that extreme comet behavior exists within natural processes. The observational window for resolving these questions is rapidly closing. On December 19th, 3I Atlas will make its closest approach to Earth at approximately 267 million kilometers. While too distant for detailed surface imaging, this represents the optimal geometry for spectroscopic analysis. The Hubble Space Telescope has been conducting ultraviolet spectroscopic observations throughout November, designed to identify specific molecular signatures and elemental abundances. Ultraviolet wavelengths reveal ionization states of atoms and molecules, providing information about temperature, composition, and energy processes occurring within the coma. James Webb Space Telescope continues infrared observations through December, monitoring thermal emissions and carbon-based molecules. Webb's superior sensitivity allows detection of dust composition, grain size distribution, and temperature mapping at spatial resolutions unachievable from ground-based facilities. The critical determination these instruments will make centers on structure. If images reveal a dispersed debris field with fragments, following independent trajectories that would strongly support natural fragmentation models. Researchers would analyze separation velocities, rotation states, and differential orbital elements to reconstruct the fragmentation event's timeline and energy budget. Conversely, if observations show an intact or partially intact nucleus accompanied by organized directional jet structures, that would represent a significant deviation from current comet physics models. Such a finding wouldn't necessarily indicate artificial origin, but would require new theoretical frameworks to explain how natural processes could maintain structural integrity while producing such extreme mass loss. In March 2026, 3I Atlas will pass through Jupiter's gravitational influence before exiting the solar system on a hyperbolic trajectory. The Jupiter flyby offers one final observation opportunity. After that encounter, the object will fade beyond detection capability, receding into interstellar space at roughly 26 kilometers per second relative to the Sun. The data collected during November and December represents humanity's only detailed record of this visitor. Unlike solar system comets that return on predictable orbits, interstellar objects pass through once. The scientific community has perhaps 8 to 12 weeks of viable observation time before signal-to-noise ratios decline below useful thresholds. This marks the third confirmed interstellar object detected passing through our solar system. The first, Oumuamua, arrived in 2017 and exhibited no detectable outgassing despite close solar approach. Its elongated shape and unusual acceleration profile sparked extensive debate. Various explanations emerged: hydrogen iceberg, nitrogen ice from a Pluto-like world, or more exotic possibilities. The object's rapid departure prevented resolution of these competing theories. The second, Borisov, discovered in 2019, displayed textbook comet characteristics: robust outgassing, a classic coma formation, and behavior entirely consistent with icy body sublimation models. 3I Atlas occupies an intermediate position. It exhibits outgassing and coma formation like Borisov, confirming significant volatile content. However, its mass loss rate, acceleration characteristics, and jet structures deviate from standard models in ways that Oumuamua's behavior did not. The combination of comet-like features with quantitatively unusual parameters makes 3I Atlas particularly valuable for testing the boundaries of current theoretical models. The object's trajectory presents its own statistical curiosity. Interstellar visitors can approach from any angle relative to the solar system's orbital plane. Yet 3I Atlas's path aligned within 5 degrees of the ecliptic, the plane where planets orbit. While not impossible, such alignment is statistically uncommon for objects originating outside the solar system. Two competing frameworks have emerged for interpreting the accumulated data. The first maintains that 3I Atlas represents an extreme example of natural comet behavior, pushing boundaries of observed phenomena, but ultimately explicable through refined models. Advocates note that each individual anomaly has precedent in solar system observations, just not all combined in a single object. The second framework suggests the object exhibits characteristics that current natural models struggle to accommodate simultaneously. Proponents argue that when multiple anomalies coincide, the cumulative improbability merits consideration of alternative explanations, even if those remain speculative pending additional evidence. By January 2026, 3I Atlas will fade beyond instrument detection thresholds. The scientific community will have compiled the most thorough documentation of an interstellar visitor yet achieved. The measurements are real. The orbital calculations are verified across multiple tracking stations. The spectroscopic signatures have been recorded by independent instruments. What astronomers document in the coming weeks will establish the baseline for interstellar object classification and inform theoretical models for decades. The results will either validate current comet physics with minor adjustments or indicate that our understanding of how interstellar matter behaves requires fundamental revision. The data will determine which interpretation the evidence supports. Until those results are released, both possibilities remain on the table, waiting for observation to resolve what speculation cannot. If you found this analysis valuable, please subscribe to stay updated on 3i Atlas's ongoing observations and what the December data ultimately reveals. Leave a comment below with your thoughts. Do you think we're witnessing extreme natural phenomena or something that challenges our current models? Thanks for watching, and see you in the next video.